Alright, so in this video I'm gonna be explaining another important article about domain adaptation, again in the unsupervised setting, and we are using the technique of adversarial approach instead of maximal mean discrepancy or other measures. But the title of this article is Adversarial Unsupervised Domain Adaptation with Conditional and Label Shift. So we have different domain shifts: label shift, concept shift, covariant shift. So these three are the most important. Of course, it's hard to decouple them. Sometimes some of them are mixed to each other and it's difficult to separate them. But here in this paper, they focus on label shift. So this paper in 2021. In this work, we propose an adversarial unsupervised domain adaptation method under inherent conditional and label shifts, in which we aim to align the distributions with respect to both P of x given y and P of y. Since labels are inaccessible in a target domain, conventional adversarial unsupervised domain adaptation methods assume that probability of your labels is invariant across domains and rely on aligning P of x as an alternative to P of x condition on your label alignment. To address this, to this end, we provide a thorough theoretical and empirical analysis of the conventional adversarial unsupervised domain adaptation methods under both conditional and label shifts, and propose a novel and practical alternative optimization scheme for adversarial unsupervised domain adaptation. Specifically, we infer the marginal probability of your label and align P of x condition on your label iteratively at the training stage and precisely align the posterior P of y condition on x at the testing stage. So this is the plots of unsupervised domain adaptation performance with different levels of label shift using this KL divergence between two distributions of source and target as a metric. Our CLS is more robust to label shift than conventional adversarial training. Maximum discrepancy, dropout, and self-train. So this is an illustration of our alternative training scheme for conditional label shifts. We infer P of y and align P of f of x condition on y. So we have source and target domain, but we give it to f, and then we have this conditional shift alignment. But we also infer probability of your target labels. As I said, we have different kinds of domain shift: concept shift, label shift, covariant shift. This conditional shift is seldom used in the literature, so that's why I don't focus on that. So the label shift occurs when the propagation of each class is different between source and target domains. For example, this reference proposes a test distribution estimator to detect the label shift. Or this reference introduces as a regularization approach to correct the label shift. And 7, consider the label shift in an optimal transportation-based UDA unsupervised domain adaptation task, which is also related to the class imbalance problem in maximum mean discrepancy. So what is the methodology? So given a source domain, P of S, and a target domain, P sub T, a labeled dataset is drawn IID from source, and unlabeled data is drawn IID from the marginal distribution of P sub target. The goal is to build a good classifier in the target domain with the training on D sub S and D sub T So for a hypothesis H, we can see that the expected loss with this hypothesis H on the target is upper bounded by this part, this one plus this minimization. And D is equivalent to Jensen-Shannon divergence in conventional adversarial unsupervised domain adaptation. So good. For any hypothesis, we have an upper bound on the target expected loss. So what is important? First, the difference between source and target distributions of your data. Also, this relation, this difference, and as well as this difference for the target. But for a target, we are conditioning on your data source minus target, but we are drawing from the target. Here we are drawing from the source. That's the only difference. So based on theorem 1, this theorem that I showed you, that we have an upper bound for expected loss of the target, based on that, and assuming that that performing feature transform on X will not increase the values of L sub t, adversarial unsupervised domain adaptation apply a feature extractor onto X, hoping to obtain a feature representation that has a lower value. To this end, to address this issue, F is trained to make the feature distributions of the two domains indistinguishable by using a domain discriminator. So this is classic here. Everything is standard. But now we first analyze how label shift affects the adversarial unsupervised domain adaptation when enforcing the distribution of feature representation to be invariant across domains. We start analysis under the label shift only assumption in adversarial learning, followed by taking a step to introduce the conditional shift. So given this probability of source and target to be the same, if a decent f makes ps of f of x to be p sub t of f of x, then we have the probability of source of their labels shouldn't match. The concept shift of f, and there exists the probability, source of y, such that this probability of a target given on f of x is invariant. So we can deduce that enforcing f of x to be domain invariant may mix the feature of all classes in the feature space, since p sub s or p sub t will be a constant for any x. Under the joint conditional and label shift assumption, there is also a conflict between minimal domain discrepancy and superior classification performance. Following the law of total probability, the optimization objective of adversarial UDA to align P sub S with P sub T can be formulated like this. Probability of f of x conditional y times probability of y equal to I. Suppose that the samples of class I are completely distinguishable from the samples in other classes. So suppose this. Therefore, the adversarial UDA is enforcing the probability of the source to be exactly the same as probability of the label of the source. So taking the integral over x sub I for both sides, we have this important relation. The probability of a source and target for any given label is the same. This deduction contradicts with the label shift assumption that we had. So this is the idea. Based on the above analysis, we have the conclusion that the label and conditional shift are non-negligible in adversarial UDA. Since P sub t of y is not available in UDA, we propose to align the class-dependent conditional distribution and estimate the label distribution following a term-based alternative strategy in each iteration. Now we are talking a conditional shift alignment. That is something seldom, as I said, seldom used in the literature, but they signify it because to incorporate the knowledge of P sub t of y to align P sub s x condition on y with P sub t of x condition on y, we introduce a class-wise balancing parameter gamma. So this gamma here is just and gamma star is the vector that makes this equation hold. So we expect that this relation holds. There is a gamma, we call it this gamma, we call it class-wise balancing parameter. It tries to balance. Therefore, we propose to multiply gamma to the source domain term of the optimization objective. So we precisely estimated gamma, we can align the conditional distribution using adversarial unsupervised domain adaptation. I think this is a Chinese article. So they are talking about conditional shift. But it's a very interesting article because it is hard to decouple these different kind of shifts, but they claim that they can do this by this gamma idea. Let's carry on. And now we configure C+1 output units to represent the C class and a target domain respectively. And the score function is defined on this space. Since the sum of probability that f belongs to one of C class is not 1, we need to reparameterize the conditional score. So they reparameterize it, and now its objective is written again like this. And then they have this proposition: the joint can lead to better approximation. Okay, here is important. Assuming the conditional distribution is aligned, so the probability of source and target of f condition of y is equal, if we can estimate the target label distribution using the marginal matching. Instead of working on raw data, in this work we carry out our analysis in the feature space. Note that P sub s of y can be obtained by counting each label sample. Targeting this, the mean matching is a simple yet efficient method. The target label proportion can be estimated by minimizing this loss function. Mu sub t is the encoded feature mean of the target. So in summary, we have 3 to be learned players in the game at our training stage. The first player is called feature extractor. The second one is called joint descent CLS, and the third one is called P sub t of y estimator. In each iteration, we update the following an alternative optimization scheme. We infer it first, fix f and update the target label distribution. Then we align it. Fix P sub t of y estimator first and update the feature extractor and joint descent CLS following the GAN protocol that you are familiar with. Finally, we obtain the target domain classifier in testing. Suppose that we have successfully aligned the conditional shift and precisely estimated the target label distribution at the training stage. The posterior in the target domain can be P sub t of y to be equal to this. Since we cannot practically know the exact gamma star, we choose the estimated P sub t of y to calculate gamma in each iteration. So these are experimental results that they use ResNet 101 for the backbone. And for CLS, they use ResNet 152. But this is for partial unsupervised domain adaptation from going from this source to this target. So we tackle the problem of both conditional and label shift in the context of unsupervised. We carry out a thoroughly theoretical analysis to demonstrate that it gives a more realistic and even minimal assumption in many tasks. Then we propose to align these two shifts, conditional and label shift, in an alternative optimization with a fade-in P sub t framework, which consists of three. As I said, we have three players in this game, so it's very related to each other. They update each other. The merit of joint parametrization also investigated. After training, the posterior alignment is applied for real-world deployment, and extensive experiments verify our analysis.